cathode ray oscilloscope. And this topic has been mentioned at least 2-3 times in the syllabus. One of them is with the title of Uses of Oscilloscope. So if I show you the syllabus, one of the mention of the topic of oscilloscope is over here. So the structure of the oscilloscope, the construction and the components of the oscilloscope that are not part of the syllabus, you should be aware of, or you should be familiar with interpreting the graphs, interpreting the traces, especially to answer for the value of time period using Y gain and time base. And what are these things? I'll explain. Question number 1. What is an oscilloscope and why do we use it? Where do we use it? And the answer is, oscilloscope is an electronic instrument which is used to display the waveforms of the signals. So this is what the internal structure looks like, but we're not supposed to study the internal structure in detail, so we're going to fast forward this thing. And the outer structure of the oscilloscope, so this is what the oscilloscope is going to look like. And the front part, it has several buttons and all of that. So this is what the front part, the buttons and all of that would look like for the oscilloscope. 3 main parts: electron gun, deflection system that includes horizontal and vertical plates, and the last one upon which the signal is displayed, which is a fluorescent screen. The trace of a waveform is seen on the screen of a CRO. There are 2 settings: vertical gain, which is in the unit of volt per centimeter, and then you have the next setting, the next knob, which is for the time base, which is in the unit of millisecond per centimeter. And then we have these traces, and you get questions in paper 1 from these traces. How are the traces of different CRO when using DC and AC supply? So if you're using the DC supply, the signal, the trace will look something like this, like the yellow line. So the vertical position of the yellow line from the mean position, okay, this is your central position. And the vertical displacement of the line from the central position is telling you the amplitude or the magnitude of the DC signal. And likewise, you can also display an AC signal. For example, here we have a sinusoidal signal which is being displayed on the screen of the oscilloscope, and this is the mean position, the dotted lines, this is the mean position. And if we can find the distance from the mean position to the maximum value, to the mean position to the maximum displacement, that would be the amplitude. But then we have to factor some correction as well. For example, we have to consider how much value is represented by a small square, and that depends on voltage gain. So now let us compare the dots. What happens when we turn off the time-based settings? So initially, if your signal was like this, and they're asking you turn off the time-based settings, keep it in your mind, the rule of thumb is, if you're turning off the time-based settings, you're turning off the x-axis movement. So there would be no movement along the x-axis. So once you have set the time-based setting off, your signal is not going to move horizontally. So this is what it looked like previously. And after you turn off the time-based setting, you see there is no horizontal movement over here in this one. Likewise, you had another signal which was displayed like this, or probably the same signal but with a different voltage gain. And once you turned off the time-based setting, the horizontal movement stopped. And for the third one, you had the same thing. Once you turn off the time-based setting, the horizontal movement stopped. It now looks like a dot. It can only move upward or downward. For example, if you move your signal upward, your dot would move upward. It cannot have horizontal motion if the time-based setting is off. Then you have a sinusoidal signal. It is moving up and down at the same up and down throughout the time. But since the time-based setting is off, your signal cannot move forward or backward. It can only move up and down. And it would move up and down in correspondence to the signal for which you have set the time-based setting off. For example, if the input signal, the same signal was moving 2 small squares upward and 2 small squares downward, then you will see from the central point the signal is covering 2 small squares upward, 2 small squares downward. So this is what happens when you turn off the time-based setting. And the bottom line is, once the time-based setting is turned off, there is going to be no horizontal movement of the signal. It can only move on the y-axis. So let's see some other diagrams, which is just for the reinforcement of the same pointer. DC input with time-based setting off. If you turn on the time-based setting for the same, so at the same vertical position, it'll now have the horizontal movement as well. So this is what it would look like. Then you have the next one, AC input with a fast time base against AC input with a slow time base. This one I'll explain afterwards. What do we exactly mean by that? So let's take a look at the next question, at a sample question from the past paper. An oscilloscope is connected to a DC power supply. The time base on the oscilloscope is switched off. What is seen on the screen of the oscilloscope? So what do you think should be the answer for this one? It could be either A or C. Yes, it has to be either A or C. In that case, it's going to be A. And why not C? What do you see for which the trace would look like this if you were having the AC signal? Okay, so where do we study this thing? Over here. If you were having the AC signal, then after setting the time base off, it would move only along the y-axis. But if you have the normal DC, so it could be upward, it's just the same. If it were with the negative sign, it would just move below the central point, below the origin. So the answer for this one has to be A. Now let's take a look at the next thing. How to determine the maximum voltage and the time period using the oscilloscope. So the first part is we need to calculate the number of boxes in the amplitude if you want to find the maximum voltage. And then we need to multiply with the Y gain. And then you can write down this formula. Maximum voltage equals number of boxes that you get from, that you count from there, times the Y base setting, times the Y setting, Y gain setting. So let's check out the graph. Let's check out the trace. So first of all, you can notice the center line, the mean position, and the mean position would be over here. How many blocks do we have above or below the mean position? You can check above the mean position. How many blocks or how many small squares do we have above the mean position? Do we have 2 small squares? Okay, so what do we write in the formula is we write 2 for the value of the boxes. So we write 2 for the boxes times the y setting. So y setting is basically telling you what is being represented by a single small square. That is your y base setting. And where do we find it? We can find it right at the top, at the bottom left corner. The y gain is at a setting of 5 volts per division. So we read 5 number from there and we read the unit from here. So 5 volts per division. This is how we read it all together. 5 volts per division. So one small square is representing 5 volts. Then we have 2 small squares. So how many volts we would be having? 10 volts. So 10 volts is the maximum value, aka the amplitude of the signal. So the amplitude of the signal is 10 volts. So this is how we find the maximum voltage or the maximum value of the signal. First we count the number of boxes, we multiply by the y gain. Then we can also find the period, the time period of the signal. And for that we use the same formula, boxes, but we multiply this time with time base setting. So period means, how do we define the time period? Time period is the time for one complete cycle. So let's see, where does one cycle complete? So your wave starts from here, half of the wave is completed. Over here, the full wave is completed. So how many small squares do we have in x direction that completes one wave? We have 2 boxes, right? After every 2 boxes, one wave cycle is completed. For example, the first one completes over here in this box and in this box. And then we multiply by the time base setting, which is 2 with the unit of millisecond per division. And this is your 1 division. One small square is 1 division. So we multiply by the time base setting, which is 2 millisecond. So what do we get for the answer? We get 4 millisecond, aka 0.004 seconds. And if you want to find frequency from here, you can find the frequency mathematically. That equals to 1 over t, which equals to 1 over 0.004, and that equals to, what do we get from here? 1.25 multiplied by 1000. 250. Yeah, 250 hertz. They ask you a lot from the graph, from the trace. The voltage gain is given, the time base is given, and they ask you to find the period, they ask you to find the frequency. And keep it in your mind, even if they ask you to find the frequency, it's always recommended that you should be finding the period first and then mathematically answer for the frequency, because finding the period is easy. All you have to do is to figure out how many small squares does a single wave take. So if a single wave is completed in 2 small squares, multiply by the time base, you get the period. From period, you can find the frequency mathematically. Frequency equals to the reciprocal of the period.